Okay, guys, we're live. Okay, so in today's Erised session, we're going to do GDB. Just going to practice GDB and basically just go through some of the common operations you might need to do with GDB. So first, you guys should have cloned this repository, and if not, you can clone it now. So for people who have done this from the last session, you can just SSH into your Vagrant box and then pull the repository to update your files. Just wait for this to log in. Okay, so if you need to update your files, just do git pull and you should update. Okay. Now, what we need to do first is to install PIDA. To do that, I'm just going to reinstall mine. You go to your home directory, just with this bit. I'm just going to remove my PIDA just to show you guys. So you guys should have a clean box like this, you know, nothing else except the Erised repository in your home directory. So all you just need to do is git clone that repository. And then add this line to your GDB init file, and it should run PIDA. So it runs PIDA. So you know that it runs PIDA because of this this prompt. If you do this, you get a lot of cool commands you can use, which we won't look at much today. Okay, so yeah. The first thing we'll be doing today is just gonna do basic GB commands. So we're just gonna try running programs, just gonna try stepping through stuff, do disassembly, we're gonna look at registers, memory, and we're gonna look at how a function call stack looks like when you're stepping through breakpoints, and then we're gonna look up file and process metadata. Okay, so to start off, we'll go into session 2, and we're going to GDB practice, and we have two files. So we're not going to reverse everything completely today. You can do that on your own. We're just going to use them as our examples. So the first thing we're going to do is, yeah, you just muted Elliot, but it's fine. Stop talking. Okay, so the first thing we do is we go into verb, which doesn't do much. It says no, and okay, in this lesson, right, you're allowed to look at the you're allowed to look at the source code, so we can kind of figure out and look at and map what's in the source code to what you see on GDB. So I'm just gonna run, and this is how you run a program with GDB. You just you set it as an argument to GDB, and it loads it. It reads the symbols and it loads that binary. So now if we've loaded binary, right, we can get it run by just typing run, or if you're lazy, just type R. So you see it returns no, and then it returns exits with exit code 1043. That's kind of odd. And if you looked at the source code here, you should have seen that it checks that argc is 4. So if it's not 4, it will just print out no and exits with this exit code. So if you put we can put arguments, we can send arguments to the program. We run it by just putting them here. So it will just run the program with these 3 arguments, and it should say something else, or it should return something other than 99. And it does. It returns with 03. So this is how you basically run a program like that. So just to verify, right, this is working. You can, if you look and reverse this program, what it does is it's comparing all the arguments to the return codes of all the return values of all the functions here, and if it all matches, it prints out yes. So anyone, okay, like at this point, and does anyone want to present how would you get something um to print out? How do you get a printout? Yes. Yeah, you're allowed to use the code, so try. So, yeah, I see how you're looking at the code. Oh wow. Okay, Elliot, you see the problem, right? You probably don't have. Are you running a 64-bit system? Okay, let me unmute you.
Yeah, yeah.
Okay, so you're running a 64-bit system, right? And that binary is 32-bit. That's why you're having problems running it.
Okay. So you need to get multi-lib.
Yeah, you need to get multi-lib. So in this case, doesn't matter.
Um,
I mean, by looking at the
okay.
code, you understand what input gives it lets you print out yes, right?
Yeah.
I mean, you can always recompile it and then just oh, let's look at Aryan. Yeah, yeah. Okay, so the answer is just to run it with bittersweet symphony as arguments, and it prints out yes. Okay, so that's how you run a program in GDB. Now on the next part, you might ask, if we already have a program running, how do we use GDB to like how do we use GDB to debug it if we already have something running? So let's say we have two windows. Let's create a window. Okay, in this window, I'm just going to go and run new order, which is another program. So if you run new order, it stops here and blocks. And why does it block? If you look at an L trace, it actually does a read. So read blocks. So it's just waiting for user input. So right now, if you do this, right, and you go into another terminal, and you look at the process list, it will be there as a process, reading process. And if you look at this is actually the PID. Because if you do PSAUX, PID is in this column. Yeah. So this is the PID we want to debug, and we can do this by using GB and we pass in the process ID. But if you do this, it will fail because it says operation not permitted. So anyone knows why this happens? Why can't we use a non-root user to debug my own processes?
I'm not sure.
Anyone want to make a guess? It's partly related to Ubuntu's kernel. It blocks even the same user um from attaching ptrace to the other memory the memory of another, sorry, to the process, to another process. It's so you can maintain integrity of that process. Yeah, so only root is allowed to do that. You can get around it by setting some kernel parameters, but it's easier just to do this. So yeah, you attach it nicely now, and you see it actually breaks here. It breaks in a kernel vcs call. If you try to type stuff in here, it doesn't work because it's now halted. It's being debugged by GB right now. So if we let it continue, it exits, and you see this one actually um it actually read ASD and then it exited. Yeah. Okay. So that's the second way to debug. Okay, so maybe you want me to repeat that? Okay, I'll just show again. You run this program, and if you look at here, here's a UX. You can see that the program has this process ID. So we'll attach that process ID with this command, and when you attach it, it kind of halts at this point. So when it halts at this point, right? Basically you can do your stuff like you can look at your registers, etc. But it's not going to be very interesting because it's within it's within this internal guts of the operating system. So you want to go back to somewhere where you want to be somewhere where you're more interested in, like user code, like main, for example. And this is where you want to kind of land. So how do you do that? So okay, let's say I'm going to use this as an example for the breakpoints. So how do you think we can land in here? Like from this point where we're in syscalls. How do we go from internal code, internal OS code to kind of user code? Yeah, we can break at a memory address. So okay, um, I present two ways to break in GDB, and in this case, look at here. I actually use break main. You can use break main if there's a symbol. So if you do like this as main like I did, can you also do break main here? Yeah, so we can break it at here with the command. So I'm going to go and delete that breakpoint. Or we can also use, since this is the address of main, we can also do this. Basically, you need this star there. It means that we're going to dereference that memory address. So we're going to stop at that memory address right now. So to do that, I'll just continue. Okay. Can anyone tell me why breaking at main didn't work? Because it's not doing anything right now. If I pass in input, it's gonna exit and it's not gonna break. So can anyone tell me why that happened? It's something to do with where I actually stopped at, where I tried to break on. So can anyone now suggest, like, okay, since I can't break in main, where should I break? Yeah, okay, so maybe just suggest an address that I can just choose. Okay, so after the read, yeah, after the read, where should I break at? Just give me an address to try. Okay, so you're gonna stop at you're gonna break here, which is, I think, it's here. So yeah, just right after the read. Okay, so I'm gonna continue this. I'm gonna type something here, like hello. And you're right, it breaks at this point. Okay, so now we know how to break at points. The next thing we need to do, okay, you can do this assembly if you want. So right now we're breaking here. We can do this as. You see that we're right here. We're just going to do PDSS because it's PIDA. Not right now you have PIDA, so it's all more awesome. It's more awesome because it has colors. That's what PDSS does, as opposed to DSS. It gives you colors.
Wow, I didn't know that.
Yeah. So that's pretty simple, disassembling. Okay, so the next thing you can do is to step through code. It's very simple. I just use step I. So you can step I to go through the code, go through the code. You can follow it. So that's pretty simple. So right now I'm in another function. So I actually step I right into a function, and you can see that it does something. So okay, maybe I'm gonna do I'm gonna step I up to this string call. So you can kind of figure out what I'm trying to do right now. Um, I'm gonna step I. I'm gonna do info reg. So when I do info reg, it doesn't really give me much. This is the vanilla GDB output. So now there's not some Karen, you asked me that why is GDB better than PIDA, right? Sorry, why is PIDA better than this vanilla GDB? So maybe this can help answer a bit. So you can see that EX actually contains a number here, right? You can see contains a number here. So in what PIDA does it kinds of it references it kinds of resolves the addresses for you into easily readable strings and stuff like that. And if it isn't a readable string, it actually shows you that this is a pointer to the pointer to now. So it lets you see multiple layers at one go instead of just this really dense, hard to look at output. Okay. So the other cool thing about PIDA, right, is when you counter a call like this, libc, it actually guesses the arguments for you. So right now, string, if you look at the man page, it actually does searching for a needle in a haystack. It actually finds a substring. Yeah. So you see that the haystack is first, and then the needle is second. So if you look at PIDA, it guesses arguments that the first argument is this hello thing, which is actually what we typed in just now, right? Hello. So this is your input, and then it checks whether the word maitre d is in that haystack, which is this part. If it is, what does it do? If it is, okay. Now right now you see it doesn't match. So if it's 0, check whether it's we're going to check. So it doesn't match. So it moves 0 to EAX and then exits and then continues and it prints out here, right? So right now what we're gonna do is we're gonna get it to print that stuff. Okay, so I won't go through that because you'll just be a bit waste of time. So let's just look at the next part. We're gonna expect some memory. I'm just gonna do something simpler. We're gonna go back to verb since we solved that already. Let's go here. So we know that verb actually has 3 strings that we want to look at. So I'm just gonna break them in just to easily, and we're gonna have like 3 strings to look at. So we break here and then we go all the way to place like for example, if I return from here, and you see that I actually have the word bitter in here. And you see that this is the power of feeder. Info reg, it shows nothing except numbers. But if you look at the feeder, it does tell you that this bitter is stored at an address. Also, how do you know that that bitter is stored at an address? So this is actually an area of memory. If you look at area of memory using um, this command, you can see that there's something stored here. There's all these numbers stored here, and these numbers are actually in ASCII, like 74, If you take this and put it into Python, for example, let me just stick one number, and since it's in a little endian, you can do something like this. Sorry, you can see it's actually the first part better. Yeah, so it's storing the value of the ASCII code in this area of the memory, in this area of memory. Now, maybe you can ask, what does this thing actually do? You can split it up into three parts. This X actually stands for examine. The 32 stands for how many of this unit do you want to examine. So like right now, you're saying we want to examine 32 words in hexadecimal format. So we're gonna do 32 words. Basically, each word is 4 bytes. So we have 32 times 4, which is this many. And we want to represent them as hexadecimal, so X. We can actually use something like O if we want, or to represent it as a octal, or we can do T to get binary. I think D does, yeah, it gives you integers like that. So the cool thing is that you can actually do an S also. It tries to read this as a C string, and it shows you the C string. So you can figure out how PIDA does it. PIDA actually does examine S to get the value um of you can get the C string out of the address. I mean, you wouldn't want to just do this all the time, right? Infrared, you see this string and you do this for everything you see. So it's really very, very convenient when you have PIDA. Okay, so next thing, okay, we talk about a function call stack. So right now we're in main. If you do backtrace, you can actually see what called us so far. So it actually started from start, then it went to libc start main, and finally we're in main. So maybe just try to step into a function like, I don't care about string compare. Let's say I want to step into suite. Oh, you don't get the suite because we don't pass the first test. So maybe just pass the first test. Let's get the suite. Okay, so we're going to bidder. We're going to return from bidder. We're going to do a test here. So we're going to do string compare with these two arguments. It's going to pass this. So it's going to go in the next test, which is suite. Okay, now we're in suite, right? Let me just press this a few times. If you do backtrace here, or BT, you should actually see that it's actually one more level of a call. So you can see that start calls, libc start main calls suite. So that's how you get your backtrace for functions. Okay, so the next thing is, this is really interesting, but if you have a very badly behaved binary that obfuscates its the stack of operations and everything, this can go totally wrong. So don't trust it too much. Okay, the next last thing is how do you look up processes and process information, how you look up file information. So if you do info proc, you can see that this is process 3748. You can see that this is the command line that it's running, this working directories and exes, and this all actually really are represented in Linux as files. So this, let me just diverge a bit. You can see that there's actually something called the proc folder here. This is all the process information. So you do proc, you do 3748, right? This is actually where all the process information is stored for that particular process. So if we cat command line, for example, you see this thing here. It's a bit hard to read, but this is kind of what we see here, right? This command line, the current working directory, and the exe is all shown in here. Exe, yes, exe, current working directory. So that stuff we can get from the file system. Now, the next thing we can look at is the shared libraries. So shared libraries, usually you have these two things, right? The loader linkers. You have your libc, but sometimes you do have other shared libraries like for example, if you need to do crypto, then you have crypto shared libraries. Okay, so the next thing is that we can see. Oh yeah, this is really interesting because when you say info file, it doesn't sound like much, right? But actually it is a lot because it shows you where each segment is mapped in memory. So if you know where the GOT is mapped in memory, you know that this is writable too. And when it's writable too, you can put your own data lab and do exploits and stuff. So another interesting thing is if you know where a libc base is, for example here, you can calculate offsets from this libc base for certain functions, and when you can do reason-oriented programming, you can jump to those addresses if you know these libc bases. But of course, these bases are all randomized with ASLR, so don't get too happy. But it is good to note that these addresses, right, for non-portable position independent executables, these addresses are constant, so you can do ROP on these addresses pretty easily. Yeah. So the next thing is checksec. This is a PIDA function a command. It does a check on the binary and tells you um what protections are available on the binary. So we can see that stack canaries are not enabled. Fortify is not enabled, but no execute is enabled. So no execute is a protection to stop the most basic of buffer overflow attacks. So anyone knows what no-ex is? Just since we have time, we just talk about no-execute.
It separates your data from your code and makes sure you can't execute data as code, basically.
Yeah, that's basically what it is. It's also known as RX or sorry,
WXOR.
WX or XOR X.
Yeah.
Okay, this one's an XOR. Yeah, WX or X. So you can either read or exclusively or execute. So you write exclusively or execute. So you can't write or and execute at the same time. I mean, there are ways around this also. Like ROP, you can also do mmap magic and stuff like that. Okay, and I also recently learned how annoying PIEs are. Basically, portable position independent executables don't have this nice constant addresses. Basically, you'll see numbers like 0 0 0 0 0 1 F here, and then at load time it will automatically it dynamically give you different addresses. It's basically like ASLR on the text segment. On the user code. Yeah, and railroad also is something read only. So this one we won't touch it yet. So I mean that's pretty much it for this session. It's pretty fast. So does anyone have any questions? Or if anyone wants to like try exploring something else, you can talk about it as well. A strip binary, you want to try that? Okay, so if you have a strip binary, so let's see, I'm just gonna pull verb again to temp. So I'm going to strip the binaries. You can just do strip like that. It's going to remove all debugging information. So if you do file verb, it says strip, right? So if you do object dump on this thing, you have no more information about anything. Basically, the whole text segment is lumped into like this. Okay, so the first thing we can do is we can maybe try choosing somewhere where it's interesting. So let's say this part looks interesting because this part looks like a string. So I'm gonna like take this address. I'm gonna run the binary. I'm just gonna break at this particular address, so like that. I'm just gonna run it with my arguments. Yes. Yeah, so we break here. Wait, did we break there? Yes, we broke there. Okay, you see when it says int3, right? This is actually not part of the code. It's because GDB inserts this int3 instruction to break. Okay, so we can step through code as per normal, like that. But you see, actually, you look at this. This is actually not accurate, right? See, it's always shifting every time I move. It's kind of being really weird. So you have to try and do stuff like this as well. You can see that at this point, what kind of assembly it looks like from when you're executing. But you still can put breakpoints in the strip binary. It's just gonna be a bit more confusing to reverse. Yeah. Anyone else have more questions? I mean, of course, for strip binary also, like I wouldn't just use GDB alone or object dump alone. I'd probably use something like Hopper to kind of do more analysis on it. So let's say I have a strip binary again. Like, I'm gonna strip this. My Hopper's taking a while to load. So, I mean, anyone else have any other questions other than the strip binaries? Okay, so I'm just gonna load this in Hopper. So you can see in Hopper, right, you have an entry point, and then there's something, an argument to main. You click on this, and this is all your code. This is all your code from before lumped into one function. But you still notice that it has very similar structure, right? Just without any symbols. So you see, like I guess just now that something's a string, like this one is probably a string. Yeah, it's a string. It's just it's not very well passed. So stuff that is very obviously strings, they do get passed by your hopper quite easily. I'm gonna follow that in here. So like bitter, it does show to be bitter here. So this used to be bitter. This used to be main. This whole thing used to be main. But you see, in strip binaries, you still have some information because it uses libraries from libc. It uses functions from libc, and then you can kind of figure out what it does. Like for example, this one you can see that it's checking some argument. This one it gets bitter, then it puts the argument on the stack as well. Then it compares the two. So it's not that bad. It's not as bad as obfuscation. It's just it means you lose a lot of debugging symbols. That's all. That's all strip does. Yep. So anyone else have any more questions? You guys figure out how to solve the new order yet? Okay, so if yeah, so I'll stop the broadcast now, so I think we covered what we want to cover for the session. But I mean, I can still stay on to, I mean, just play around with whatever you want to ask. If you're curious about anything, just ask.